Well, good evening, everybody, and welcome to our lecture tonight. I think, as you can see, it's not quite the straightforward way of doing things, because tonight we have the Clough Award to be presented. Or should I say the Clough Medal, get it right. How many carat gold? Don't know. Anyway, you may wonder why this image has a railway in it. And I thought I'd introduce Clough by telling you what this has to do with Clough. The sad truth is that when Clough died in 1916, he was doing field work. He was doing winter field work for the survey, and he was working on the rocks that are at the far end of this station platform, and the cutting you can just about make out. And apparently he didn't hear the train coming in our direction from uphill, it was said, and he was run down, and they got a special locomotive to take him to hospital somewhere, and unfortunately he died a couple of days later. So Clough was killed here and ended at the age of 64, was it? I can't remember now, 64. His, I can't read that from here, you see. The Clough Medal and the Clough Award as well all honor this distinguished geologist who was well known in the Highlands particularly, but the winter job brought him down to the lowlands, and unfortunately to the what is now the Bowness and Kinneil private railway. And the plaque you see on the other side was made by us, the society, and hung in the station building at Burke Hill. Unfortunately, I can't remember now whether there was a fire or whether there was simple vandalism, but this, along with other things, disappeared and hasn't been replaced. Maybe we should think about replacing it and honoring him again. So anyway, Clough, this very distinguished geologist, we've got the medal, and tonight we're going to present it, and we're going to present it to Professor David Evans, and I'm glad to see he not only has himself, but his wife Tessa to support him, and at least one student who was found wandering around the building. So with that in mind, I'm going to ask John Merritt to come forwards and tell you a little bit about David's achievements. And at the end of that, I will present the method.
Thanks. Good evening, everyone. And it gives me very great pleasure to welcome Dave here this evening. We go back quite a way. In fact, we go back a very long way, because we probably first came across each other in the swallow holes at Water End in Hertfordshire, a famous locality, fascinating locality. It probably inspired us both to get into physical geography and geology. I would have to say that when Dave was there, he would have been in short trousers and riding a chopper bike, and I was walking the family dog at the time, but so that's how far we go back. And of course, since then, Dave's now become a leading quaternary and glacial scientist, both in the UK and worldwide, and has made an enormous contribution to research in glacial geomorphology and glacial geology. And he has a prestigious publication record. That's 200 peer-reviewed papers and 16 textbooks, all of which, like this is the lightest one in weight I've brought this evening, but they're absolute Bibles for all us quaternary geologists these days. And it says a practical guide, and that really sums Dave up. What he produced is very practical, very useful, bringing lots of information together to help us all. And Dave was at Glasgow for like 14 years, Dave. So the department there, but since leaving, he's still kept up close association with the teaching and advancement of earth science and physical geography in Scotland. And now, of course, he's at Durham. And he continues to eagerly promote, support postgrad research, and has a large number of students that have he's supervised over the years, and some of which are in the audience today. His main fields of research have been glacial land systems, using his knowledge of high Arctic and mid-latitude mountain ranges to develop conceptual models to understand glacial process and how landforms, glacial landforms are created. And that's very appropriate, where we're here in Edinburgh, we're surrounded by a legacy of the last ice age. Every hump and bump, every moraine, every mound of sand and gravel has a story to tell. He's also helped incredibly with the understanding of glacial sedimentology. And here we're in Edinburgh, building on the work of Jeff Bolton and many others in this department, and provided this practical classification of glaciogenic deposits, which is very useful to us all. It had an early association with the Brit Ice project, a lot of you will know about, which is championing the capture and review and dissemination of an enormous amount of published information, both written and in map form. And so that's another of Dave's field, is bringing together a lot of information and disseminating it. More recently, he's been involved with the engineering group of the GeoSoc, bringing together experts in glacial and periglacial geomorphology, quaternary history, engineering, geology, and geotechnical engineering, in order to establish a best practice when working in former glaciated and periglacial terrain. And there's a recent publication which would be much used in the departments in coming years. And he's also thinking of this traditions of this department here. He's the lead author of the Quaternary chapter of the Geology of Scotland, which is going through another edition. Is it 6th edition, is it, Graham? No. So all in all, I think Dave's a very extremely worthy recipient of the Clough medal. He's worked not only in Scotland, but Northern England, which is included in the remit. So without further ado, I'd like to welcome Dave up here. Hand over.
Okay. Well, listening to that introduction, I can well see why Dave has been nominated for the Clough Award. I'm sure I'd never achieve all of that in my lifetime anyway. So, Dave, I'd like to present you with the Clough Award in solid copper coated in silver, I'm afraid.
Super.
Yeah.
Thank you very much.
And your what you asked to get written is written on the edge of the large coin, you might say.
Right, brilliant.
So
Thank
having
you.
done that, I think they want to take a photograph.
Oh, yes, thank you.
We'll now ask Dave to give his lecture. And do you want me to give him a microphone, or are you going to be working with us?
It's got a mic on. I've got one on. I've got one on.
Okay,
Yeah.
thank you.
Yeah.
I'll switch this off then.
Great, thank you. Thank you very much. Indeed, a great honour for a geographer to be standing here in front of a group of geologists who have given me an award for working on glacial geomorphology. Probably ever since I started doing my PhD, I thought that I've actually moved a little bit away from geography, more towards geology, when I started working on sedimentology. And back in the early 1980s, it was made very clear that you couldn't really understand very much about geomorphology without looking at sediments. So at the time, sedimentology in the glacial realm was starting to develop, to grow. And I latched onto that fairly quickly because the sediments were, to me, seemed extremely interesting and allowed me to make better interpretations of geomorphology. So I come at this from a geographer's angle. There'll be lots of spatio and temporal thrown in here and there to give you that flavour of geography. But I've also thrown in a fair bit of sedimentology, because clearly that's something that you guys will want to hear a little bit more about. So the title, Quaternary Glacial Geology and Geomorphology. I'm going to talk really tonight about how we use modern analogues, that's modern glacier systems, to make interpretations of palaeoglaciology, and that's quaternary glaciations. And obviously there's a large element of sedimentology, modern sedimentology involved in that. I'm hoping this is going to move on. Got it. Okay. So I thought I'd start off with some fairly basic stuff. Again, as I say, I'm a geographer, so I'll come at this from a geographer's angle to start with. And I thought I'd start off firstly with giving you a rough breakdown of how we go about doing all of this. In terms of geomorphology generally, we really want to, in order to understand what we're seeing in ancient landscapes, we want to know something about process. And so we wanted to talk about process geomorphology. Now, in terms of methodologies, the theoretical side of this is actually what we would refer to as actualism. You guys would also use the term uniformitarianism. And what we want to do in order to come up with the accurate interpretations is we want to come up with a quantification of process. And that really is a serious problem in glacial geomorphology. It's easy to come up with measuring process in fluvial geomorphology, because I can just go and stand in a river and I can look at the processes taking place, just as an example. In glacial geomorphology, that's quite difficult. So therefore, we have a very small number of measurements of process in glacial research. And it usually comes down to tunnels through glacier ice, boreholes through glacier ice. That sort of approach is actually quite remote from the process at the glacier bed, for example. So what we tend to do, what we have tended to do over time in glacial geomorphology is use what we'd like to refer to as quasi-actualism. It's not really quite actualism at all. So we tend to go to modern glacier forelands and we associate particular landforms and sediments to processes that we can see operating on an annual basis, for example. So the classic example of that is this diagram in the middle, which is one of Bob Price's diagrams, the guy whose job I took over when he retired at Glasgow all those years ago. And Bob Price came up with this model. It wasn't necessarily new at that time, but he actually had a number of ongoing process observations at the time, which gave it more credibility. And it's a relationship of push moraines at the margin of a glacier and its association with flutings and subglacial sediments, or till, being deposited near the margin. And that model was related to observing things that were taking place at a glacier margin on a present-day basis, in a contemporary setting. What we tend to do over longer time scales to put longer pictures together in terms of overall processing in reproducing ice sheets, for example, is we use another geomorphological term, the ergodic approach, which is substituting space for time. And I'll give you another classic example here, cirques. And this is the diagram on the bottom right-hand side there shows how a cirque evolves over time from stage 1 through to 5. So we think that cirques erode into the landscape over time. they cut back into mountains, and they cut down through mountains. So we are simply observing landforms at different stages of their production and assuming that we can put them together in a sequence. We don't know it's right because we need hundreds of thousands of years to measure that process. So this is what we call the ergodic approach. So we're looking at landforms at different stages and then piecing them together. So those are the two approaches that we would take. We would want to get some actualism, some process quantification. We do that very remotely in a small number of cases. Most of the time we rely upon quasi-actualism, and when we get to longer timescales, we'll have to go through the ergodic approach. Now, in order to do this in a holistic way, what I tend to do is to look at what we call land systems. And I think some of you may have heard the term land systems before, because it was a term that was coined to summarize whole glacial landscapes from an engineering viewpoint. And so the term land system is employed by engineering geologists since the 1940s, really, but really took off in the 1970s. And the glacial land system was one of those holistic approaches to summarizing sediments and landforms in time and space. Now, what I'm going to attempt to do is I'm going to attempt to show some movies tonight, just to keep you awake, and also because they give me a bit of a break. So here's the first one. Again, some of you may have seen this before. That's not going to work. I'll have to come out of that maybe. I knew that would go wrong. There we go. Back to that. There we go. Has that gone wrong? Have I hit the wrong button? Do I hit OK? Yeah, it did work. You're right. Yeah, so I knew it would go wrong.
So this.
So if I
wasn't at play, I don't know.
No, I don't know why it wasn't playing.
Yeah. So anyway, we'll share it.
Apologies to those of you who are watching from afar. Okay, it should work like that. There we go. I'll just make it. We're going to make it bigger. Make it bigger.
Yeah, it's just
Yeah.
maximize that.
Right.
Brilliant.
Hopefully, every time I hit a movie button, it won't do that, and I won't need help. They are worth it, these, because they give you a good impression of generally what we're trying to do and what we're talking about. As I say, some of you will recognise this. This is from a paper by Alan Hubbard and friends back in 2009. And I like this one. There have been more recent models of the British ice sheet, but I like this one because it's nice and colourful, and it really gives you a very good idea of what we're trying to do. So the end game, if you like, is quaternary paleoglaciology. It's doing something like this. It's reconstructing the growth of an ice sheet through time. And the beauty of this is it shows you how ice sheets are not static and how they evolve very quickly over time. And it shows you also where ice sheets grow. And the blue blobs largely are giving you an idea here of how mountain ice-filled upland areas produce the ice first. That ice advances and it coalesces and it produces an ice sheet. And you can see running along at the top left-hand side the time, and it relates to thousands of years ago. So it runs us through the last glacial cycle. And you can see that throughout the last glacial cycle, our ice sheet was, well, the British and Irish ice sheet and all the various components of it at stages when it was more reduced into mountain ice caps. It's a very dynamic system indeed. And so therefore, the signature, the landform and sediment signature that we see will relate to the amount of time the landscape is occupied by glacier ice, and it will also relate to whether it's upland ice, lowland ice, whether it's under cold-based conditions, warm-based conditions. There are a whole number of characteristics of glacier ice in the landscape that we need to understand in terms of these process form models in order to be able to reconstruct glaciations through time. Okay, I think that's run through. Hopefully you've seen that, you've got the message there with respect to dynamic ice sheets. Now what I'm going to try to do is to get back to the slideshow. I'm glad somebody's here who knows what somebody knows what they're doing technologically. Brilliant.
So are we in the right slide now?
Yeah, just go back to that one. That's fine. Okay. I'm going to predict the next film works okay because I think it's all right. I embedded it into the slide. So, so that's the basic approach to glacial geomorphology, and the model that I've showed you is the end game. We're going to come back to the end game again at the end of the lecture. What I want to do now is I want to show you how we get to a situation whereby we have confidence that that model of the British Irish ice sheet is pretty close to probably what did happen. So, firstly, then I thought I'd give you a quick rundown of what a land system is to show you what I'm aiming to produce in the longer term, and give you a bit of a history behind all this as well. What is a glacial land system? The land system is an area of common terrain attributes, different from those from adjacent areas in which recurring patterns of topography, soils and vegetation reflect the underlying geology, past erosion and depositional processes in climate. And so what we're trying to do here is we're coming up with, as I said, is a holistic model which covers all the components rather than individual landforms, all the components which go together to give us a paleoglaciation signature. Now, similar to that would be something called a process form model. The first of these, which really came to the fore with respect to these holistic approaches, was Clayton and Moran in 1974. And this is their reconstruction of the margin of the southern Laurentide ice sheet. And a process form model is a similar sort of thing. Both these things are taking us in the right direction in terms of reconstructing paleoglaciation. This is a conceptual model that emphasizes the genetic interrelationships of specific landform sediment associations. And that works at both local and regional scales. And it allows us to link processes and forms, known process and form linkages. So, why bother with all of this? Well, here's a list of justifications. Each land system that we're looking at is a representation of glacial signature that's tuned to things like the glacier itself, the morphology of the glacier, its thermal regime, the glaciation style, the local to regional climate regime, latitude, altitude, all the things about where a glacier operates. Secondly, land systems treat landforms and sediments as associations in what I said before is a holistic framework. So we don't have to treat landforms in isolation. We put them all together to come up with a reconstruction. And land systems allow us to appreciate that glacial landform and landscape legacy that there in front of us in the geological record is a product of a spatial temporal continuum. And that reconstruction of the British Irish ice sheet shows you how that works. So that means we can build up a family of land systems which hopefully are reflective of all the different types of glacier activity on the Earth's surface. And so on these little diagrams below there, these are all the various ones that we've come up with in the past that relate to these styles of glaciation. So the active temperate model on the top left-hand side is the one you're probably most familiar with. It's quite often it's put in textbooks as representation of lowland glacial geomorphology. It's individual push moraines retreating from a landscape, exposing eskers which infill tunnels in the ice. And these are glaciers which are responding or are tuned to climate on a seasonal basis. We then have surging glaciers, ice streams, subpolar glaciers, plateaus, mountain valley land systems. We can now come up with reconstructions of what we call the glaciation styles. And the only way we can come up with these families of land systems is by studying modern glacial settings or modern glaciers. And then hopefully, in the geological record, we can spot these patterns, these spatial and temporal patterns. Okay, that's all the introductory stuff. What I want to do now is I want to show you some real empirical, some data, some observations from modern glacial settings. So I want to go through some modern analogues, and I'm going to start off with one that we've actually only just recently finished working on. And it is a glacier in Iceland called Fjalsjökull. I'll be going to Iceland quite a bit. I'm hoping that does work. That's good. So this is Fjalsjökull. It's an active temperate glacier in Iceland, and it has retreated from its little ice age maximum, which is around the outside in here, in this area here, since about the 1890. And more recently, this area in here, which is marked in as blue, has been exposed over the last 10 to 15 years. And this Google image, which is an oblique image, is that area in here. And we've got a whole series of eskers exposed and outwash fans, dead ice sitting in here. And just beyond it, in this outwash area, we have a whole load of collapsed outwash with big fractures and kettles opening up. And that's what it looks like on the ground. Now, for these maps, we use a colour scheme in the Icelandic maps, which follows the tradition of the University of Glasgow topographic department, science department, as it was. And I've followed that colour scheme just to keep things compatible over time. So where you see yellow, it's glacial fluvial outwash. Where you see orange, it's till and fluted surfaces, so subglacial sediments. The black lines are push moraines, and the red areas are overridden moraines. And eskers, you probably won't be able to see the esker symbols, they're little tiny arrowheads, but we don't necessarily need to go into that much detail. So what I'm going to look at here are glacial fluvial process form regimes. So we're looking at processes, we're looking at forms, relating them to processes, again, in this quasi-actualist way, if you like, because we're looking at things being exposed fairly recently. And this is where I'm hoping this guy is going to run for me. Yes. Look at that. I knew we could do it. Right. So this is a UAV imagery, and it gives you an overview of what this landscape looks like at the present day in a rapidly retreating ice margins in modern in relationship to modern climate warming. And as we zoom across this landscape, you can see a whole series of eskers emerging. That's the dead ice at the bottom there as we go across the proglacial lake. And as we fly across this landscape, we see a whole series of individual ridges emerging through outwash surfaces, which are collapsing. You can see the tension cracks, which are picked out by the moss and the vegetation growing on the surface there, and the kettle holes. And as we now fly out from the ice contact face by the former lake, the lake surface, we move into the ice contact outwash surfaces, and you can see these guys collapsing and opening up with the big tension cracks. So as we now move out into the proglacial outwash, we're moving into a terrain that was deglaciated back in the 1960s. And up to about 10 to 15 years ago, this surface was a totally flat outwash surface with undisturbed grade plains on the top of it. As I've been taking students to this site for the last 10 years or so, these great big holes full of water and the big tension cracks have been opening up from one year to the next, getting bigger and bigger. And this is essentially modern climate warming, melting what is essentially permafrost. Buried glacier ice underneath this surface has been buried by the outwash over time, and this is now the accelerated warming has created accelerated melting and collapse of those surfaces. We had absolutely no idea there was any ice underneath this outwash surface until this started to happen. And it gives us the impression that a lot of the processes and process form regimes are actually showing us a delayed response. So the ice, we've worked out the ice that's underneath this outwash, which is now collapsing, dates from the 1940s, and it's been sitting underneath the outwash since that time. Okay. That's the end of that. That's the end of that flight. So hopefully we will now move on. Just wait for that to stop. Hopefully give you motion sickness by looking at as it finishes off its flight. Good. Okay, so if I was going to take a ground overview of that area that's been exposed over the last, up to about the last 20 years, we can see the ice there over on far right-hand side. This glacier and this glacier here have uncoupled and retreated from this area in here, the foreland in here. This is the outwash surface, which is now collapsing. These are the eskers, which feed into the outwash surface. And this is a view from the other direction. So there's the outwash, what we call the outwash head. the ice was sitting up against this, and these eskers filled in the ice sitting over the top of this area in here, what we call this over deepening. And these eskers are changing year on year because they have ice cores within them. And this is one little myth I'd like to dispel tonight, because I think it's been a long time we've been trying to dispel this, and Bob Price tried to do it back in the 1960s. And that is that eskers most of the time are not developed in subglacial tunnels like people would have you believe. Most of these eskers are produced in end-glacial tunnels. And the reason we know that is because these guys are changing their height of them. The height is changing all the time. They're dropping all the time. And the reason they're dropping is because ice makes up the core of these eskers. And so therefore they were produced in end-glacial tunnels. As the ice is melted down, the eskers themselves have protected the ice underneath. And gradually that ice is now starting to melt, even though the eskers have been exposed for some 10 to 15 years. Okay, so what we're trying to do here is we're trying to come up with some historical reconstructions. And the reason I'm going to use Iceland quite a bit tonight is because the Icelanders have been taking aerial photographs way back to the 1945 photographs were first taken by the US Air Force. And since that time, aerial photographs have been flown on a regular basis. And you can see these guys, these are not really ortho photos, they're sort of pseudo-ortho photos. They are aerial photos draped over digital elevation models. And they take us right back to 1945, and they show how the two glaciers, Hrútajökull and Fjalsjökull, have uncoupled over time. And as they've uncoupled, they've exposed this large proglacial area with the lake up in here, as it appears, when the lake first appeared here in 1964. And then you can see that by the time we got to 1988, it was quite a large lake. And then by 92, the lake had disappeared and it had almost been infilled. And the reason it had been infilled is because in the mid-1990s, these glaciers re-advanced. And they re-advanced by bulldozing into a whole load of dead ice. And that produced a whole series of things we call thrust moraines, which are just blocks of ice and sediment which have been bulldozed forward by the ice re-advancing. So by the time we get to 2014, which are the photographs I've just showed you, these eskers and the outwash fan I showed you there earlier have developed by this point. And what's happened in here is the lake has disappeared catastrophically down a spillway, which it did in 2003 to 2004. And then this lake drained, and the eskers start to appear on the floor of the over deepening in front of the ice. So if we want to summarize all that in a sequence of maps, same color coding again. So I've now produced a sequence of maps of how this is evolving over time. We can reconstruct that proglacial landscape, and we can make some observations as to how glacier fluvial assemblages, which quite often we'll usually use the umbrella term Cayman kettle topography, have evolved over deglaciation. Now, I'm not going to go into too much of the details on this because I could talk for hours on that. I'll just summarize it with these cross-sectional diagrams. And these are cross-sectional diagrams which show us how these two glacier snouts have evolved over time. So on the left-hand side, Fjalsjökull, on the right-hand side, Hrúta. And it shows us how the ice has down-wasted and retreated over time. We then deposited a whole load of glacier fluvial outwash. And this is the best example, really, Hrútajökull. The outwash is deposited and buried glacier ice. Then in the mid-1990s, the ice re-advanced and it thrust and stacked a lot of this stuff. Then we went through a whole melt-out sequence. And more recently, what's happened is the old ice, not only the old ice has been melting, but also the glacier tectonically thrust ice has been melting to produce this chaotic assemblage of Cayman kettle topography, which is what I showed you in that movie, the UAV movie. Now, I'll come back to these a little bit later to show you how we might apply these to ancient landscapes. I just want to summarize that in terms of how we are now being able to quantify this by repeat aerial imagery, which we're now doing through UAV, through drones, using drones to take the photographs. So you can see now, since 2014, we can repeat the surveys and come up with digital elevation models on a year-to-year basis. And we can quantify the amount of surface change. So the amount of surface change here relates to the amount of ice that is melting out of this landscape, which visually you can see by the expansion of the lakes, these kettle lakes, which are getting larger and larger as we go through the sequence. And this really is picking up on what Bob Price and colleagues at the University of Glasgow did back in the 1960s when they came up with these diagrams. And these diagrams show how outwash burying glacier snouts eventually collapses to produce what essentially was kettle sander and then came in kettle topography. What we're also identifying are eskers, which are emerging through some of this. And again, Bob Price and co-workers back in the 60s, they picked out that eskers over time on some of these forelands, their surface, their summits are dropping. If you survey them over time, the summits will be dropping by several meters per year, indicating that this is all, if you like, a huge karst system, like limestone karst developed within glacier ice, which is melting out and collapsing over time. This guy over top left is at Breidemurkjochel very recently, 2018 and 2022. The amount of change has taken place in 4 years. The photograph is the same area. There's the glacier snout here in 2018. Outwash surface, burying the glacier snout, starting to pit in here and collapse. And by 2022, it's opened up into this assemblage here. Now, just for your entertainment, let's show you, this is, we actually flew this just this last summer. This is, again, another flight. Glacier ice now is the dark stuff to the bottom and to the left, so that's debris-covered ice. And what you can see in the middle ground there is an esker. The esker is emerging from the fractures in the ice. And this view will take us around and it will show us how that esker system is feeding directly into the pitted outwash at the top. And within the pitted outwash, you can see the eskers emerging. Now, the beauty of this is that when you have a look in this area in here, you can see the tunnels opening up, the eskers coming through the tunnels. But also that's interesting is you can see the tunnels have changed position. So the eskers are quite a complex system. It's quite often, again, believed that these guys represent tributaries, which are all operating at the same time. These images show that's clearly not the case. The tunnels are actually changing position quite significantly to produce the different ridges within the esker system. Okay, as you can tell, UAVs have been a bit of a game changer when it comes to looking at glacial landscapes and mapping glacial landscapes. So too, obviously, of the increasing rapidity with which satellite imagery is being used. Okay. Right. I'm going to give you another example now, which is a glacier called, another Icelandic glacier, a glacier called Quaternary. I'm going to show you this one because it's an example of a glacier similar to the sorts of glaciers that occupied the Scottish Highlands during the Younger Dryas. This is a glacier which has got a high debris load, a relatively high debris load. And so it produces not just Cayman kettle topography, like I've shown you in the previous glaciers, but also hummocky moraine. And the term hummocky moraine is another one of these catch-all terms referring to the hummocky topography in front of receding glaciers. Now, in order to understand how that terrain evolves over time, it's important again to see how one of these glaciers, how it produces these deposits over time. So again, I want to cut a long story short, the long story very short here. This is the ice margin. There's our debris load on the glacier snout off in the distance. In 1945, this is what it looked like. In 64, again, based upon our repeat aerial photography, and in 2003. And notice that our medial moraine debris and our lateral supraglacial moraine debris here is coming down through the system. And what tends to happen, because this sediment is delivered by individual rock avalanches onto the glacier snout, it comes down in what we call slugs. And so a slug of this stuff comes down to the snout stagnates, and locally stagnates under that debris load, and it produces a series of these hummocky moraine bands in the landscape. How does all that sediment get in addition to rock slope failures onto the glacier? We have a whole load of debris bands which come up through the snout. And this is our model of how we think these evolve. We've got debris coming from the accumulation zone. We've got end glacial and superglacial drainage networks. We've got hydrofracture infills. And we've also got a process referred to as supercooling, which is where subglacial meltwater being under pressure and being forced to run up slope against the topography, and that's the basal topography, that's the bedrock there, where the meltwater under pressure is forced to go up slope, it depressurizes and supercools and freezes back onto the base of the glacier, freezing sediment in. So in that way, we can produce glaciers with large debris loads. And that's what the glacier snout looks like. I think I took that photograph this year just gone, I think. So this is a hummocky moraine area, a hummocky moraine band, and that was the one that was being created in the 1960s, around about the 1960s. But it's a little bit more complicated than that. Rather than just being hummocky moraine produced by stagnation, if you evaluate the changes over time, so here are the aerial photographs, and the areas marked A, B, and C on the 1945 photograph relate to the hummocky moraine bands that we could see on the 2003 photos. So that's essentially how they've evolved over time. So we've got these slugs of debris coming down through the system. And the term that's been used for that is the term incremental stagnation, whereby an active glacier is producing areas of stagnation because of these slugs of debris. So it doesn't mean to say the glacier is stagnating. It is just certain parts of the snout will stagnate once the ice is down wasted and treated from them. So we worked out the importance of this by doing these things here. These things are called DEMs of difference. So they're digital elevation models based upon the aerial photographs extracted from one another, like the heights extracted from one another, to work out how the surface changes over time. And we're assuming that as the ice is melting out underneath the slug of debris, the surface should just keep dropping. If it's true stagnation, the surface will just keep dropping until we get this chaotic hummocky topography. Now that certainly was the case. So if we look at the color coding here, anything which is in the greens and the yellows is negative. So the land surface is dropping. And the image here, this semicircular area here represents this area, roughly this area in here. So 1964 to 1980, again, generally our surfaces are dropping, but between 1980 and 1998, I start to get oranges and reds, and those show that the land surface is going back up, and it went up by about 10 meters. The stagnating topography went up by about 10 meters. Now, bear in mind what I said earlier about the mid-1990s in Iceland, when glaciers re-advance, and they re-advance in a period of about 5 to 7 years when climate conditions were conducive to positive mass balance. So there was a cold period between late 80s to early 90s, and the glaciers responded to that. So lo and behold, rather than stagnating, what happened is the glacier pushed into the ice-core topography and pushed it all up, bulldozed it all up, which really took us by surprise. We didn't realize that was the case until we actually looked at the DEMs of difference. Then after 1998, normal surfaces resumed, down wasting. So this is what we would call incremental stagnation. Okay, next little example I want to show you, quite different again, as surging glaciers. And this little model here, this is our land system model in the middle. And here we have an assemblage of landforms, the most impressive of which I've got here in photographs, which represent glaciers that surge, i.e. they move forward rapidly over short periods of time and then just stagnate for longer periods and then surge again. Then they're not coupled to the climate, just like our active temperate glaciers are. So again, a map, this is based upon Brewer-Jochel on the northern Vatnajökull ice cap. And again, same color codings. What you won't see here are lots and lots of individual push moraine ridges, because all you get is a moraine produced every time you get a surge. So 1890 and 1963, this is an overridden one in the middle, which we think relates to a period since 1890. So the classic landforms here, the most important ones are thrust block moraines, which are these guys here, glacier tectonic features. They're not necessarily often made of glacial sediments. This one is made up of rolled up bits of outwash and peat. So the ice is bulldozing sediment in front of it, like roughing a carpet up. Very long flutings, which represent fast glacier flow. Crevasse squeezes, sediment squeezed up from the bed into crevasses because the ice fractures as it surges. And these things called zigzag eskers, which are eskers deposited in the ice, guided by the fracture patterns. So they're not meandering like regular eskers. And these are all indicative of surging glaciers. So if we're very clever, on a foreland, a glacier, modern glacier foreland, and hopefully in the ancient glacial record, we should be able to differentiate between active temperate glaciers, glaciers are responding regularly to climate, and those which are not, i.e. they're surging. And on the Braidemurkiochal foreland, which is the classic active temperate glacier setting, again, we use one of our maps. The individual black ridges here represent push moraines. And we originally thought that this part of Braidemurkiochal was an active temperate glacier until we started spotting indicators of surging. Crevasse squeeze infills, crevasse squeeze ridges on aerial photographs, which this is from a Google image, and overridden thrust block moraines. I don't know how I can get rid of that bar at the bottom there. Can I get rid of that bar at the bottom? Sorry? I'm glad somebody knows what they're doing. Brilliant. There we go. So that means you can see what the image at the bottom shows, which is a whole series of heavily disturbed glacier tectonized, folded and thrust outwash deposits, sands and gravels, which have been streamlined and overrun. So what we're actually looking at this part of the Braidemurkiochal is a mini surge signature, whereby the glacier is trying to respond on a yearly basis to climate drivers, but every now and again it's undergoing a mini surge, and we're picking that up in our landform signature, which was confusing us a lot for a long time. Now I've mentioned active temperate, so I will now give you a linkage between active temperate glaciations, moraines, and tills, and then we'll get into some sedimentology. So here, if I go back to Bob Price's model, which he produced in the 1960s, and the aerial photograph on the left is a 1965 aerial photograph of the margin of Paleoglaciological, and the multiple push moraines, which are just beautifully set up here, one per year, representing the ice moving back 2 steps, moving forward 1 step each year as it retreats. That's what we call active temperate recession. The photograph at the top is one that Bob Price gave me many years ago in 1965, of one of the glaciers one of the moraines being produced. And the photograph in 2017 is one of mine. Glacier still doing the same thing as it's retreating, pushing up an individual push moraine every year. And what's happening here is we're looking at submarginal squeezing of the till underneath the ice to squeeze up and be bulldozed forward, which is essentially what Bob Price predicted in the 1960s. Now, more recently, we've been mapping these out in some more detail, and again now using UAVs to get this, and also LiDAR imagery to get these beautiful images of glacial landforms. I just love this stuff. I mean, you have to love this, don't you? But there's flutings. Those flutings are about this high and about this wide, and the push moraines you can see here, we've mapped this. This is the area they've been mapped from. This is the glacier margin in here, and we've identified, because we now go back there every year, we can see what's going on. We've realized that they're not being produced one every year anymore. They're now being produced 2 or 3 every year. So the ice has become so much more dynamic that it's not just responding to seasonal climate, it's responding to individual meteorological events. So when we have high rainfall events, the ice is speeding up, re-advancing, even during the summer when it should be retreating, and pushing up these small moraine ridges. So we now have models that suggest that pushing and squeezing of sediment are both operating, but squeezing dominates in summer when the sediment's wetter around the margin, and that works in the same way that Bob Price was suggesting. But what we're looking at now is a slightly more nuanced model, which indicates to us that we're producing more than one moraine per year. So we can no longer count them backwards and say, oh, that was, that was we could in 1960s and the 1980s, but now in the 2000s, it's not so easy to do, because in one year we might produce one, other years we might produce two, other years three, depending on the meteorological events which are impacting on the dynamics of the ice. Okay, let's now get onto some how this is important with respect to our sedimentological and stratigraphic record. The beauty of the mid-1990s re-advance in Iceland was that we were there to see it. And at the time, we didn't realise what was going on. The ice margins were re-advancing. I always put Tessa, my wife, in somewhere so she gets, there she is, look. Long time ago, 1993. And at that point, you can see the glacier ice is bulldozing up over the moraines. It's re-advancing at this point in the summer. Went back in 2003, and this is the site. The ice is now long gone, but instead of producing one little tiny push moraine, it produced 5, one on top of the other. The ice was semi-stable because of that cold climate, the 5 or 6 year cold climate snap. And so it produced for us a stratigraphy of tills, one on top of the other. And so we came up with this model, and what we were looking at, because there were colder conditions, we were at the other end of the extreme, rather than the multiple moraines being produced each summer because of meteorological events. What we're looking at here was the ice freezing on its till submarginally in the winter, displacing it along a décollement zone, a failure zone, and dragging it forward, and then the final piece of deformation towards the end of the sequence to place the slab. You would then repeat that year on year to produce the full sequence. As I said, I'm not going to go into these diagrams in detail, but this is our sequence in terms of a full seasonal cycle. And we could explain bigger moraines and thicker tills in this way. And this is one thing, one message I want to get across to you tonight, and this is relating to till sedimentology generally. All of you in the room, I'm sure, are aware of boulder clays and how boulder clays represent glaciation, and boulder clays can be 10, 20, 30 meters thick. So based upon the images and the photographs I've just shown you, and this is a question I was asking myself for many years before I had to start thinking about this in a different way. Modern glaciers don't produce tills 10, 20, 30 meters thick. So the things that we're talking about, which are tills that are that thick, must be related to this process, whereby we're stacking them because ice margins have become semi-stable, if you like. Now, you might not think that's rocket science, but the problem is that quite often we don't see the tills the tills cannot be separated in terms of individual units like this, slabs, which represent a seasonal signature. Usually they're 10 meters worth of what we call massive diamicton. They have no indicator of any break in the sedimentary signature at all. So let's just finish it. Let's summarize a bit on the push moraines. These are our classic models of push moraine formation. And this is how we now understand how glaciers produce moraines and how they produce submarginal tills. And they produce their tills in submarginal positions. So we have the squeezing model, which Bob Price introduced in the 1960s. Pushing and bulldozing, which Martin Sharp wrote about in the 1980s. And then our model of which is a hybrid, which includes a winter freeze-on mechanism, which operates more in colder environmental conditions. Right, let's then get into some of the nitty-gritty in terms of tills and till sedimentology and till as a geologic climatic unit, because that's what it is. That's what till is regarded as. So I want to reconcile glaciology, modern process observations with till deposits in the geological record. And I need to start off here. It seems entirely fitting in this building to refer to Jeff Bolton and the work of Jeff, particularly the Bolton and Hindmarsh paper in 1987, which was the subglacial deformation experiment at Breiðamerkurjökull in Iceland. And the diagram on the top left shows the results of that experiment, which was an experiment to get markers into the deforming layer beneath the glacier and to chart the deformation of those markers from their initial vertical position to this exponential curve, which showed the deformation in the till, and that's the white area, which they call the A horizon, downflow, from right to left. The B horizon was also deforming, but the B horizon was deforming by ductile deformation. So by brittle deformation, the A horizon by ductile deformation. Now, this was important in glaciology because it was regarded as a paradigm shift at the time, because it recognized the third glacier flow process. We had internal deformation, basal sliding, and now we had deformation of the bed. And from that came models of how we might explain flutings, these long, that thing I showed you on the image earlier, the long straight parallel ridge features made of till. We think the sediment is deforming upwards into low pressure zones on the downflow side of embedded clasts. It's a lot more difficult than that, but I'll keep it for that time being, because that will keep it simple. Now, the photograph here was taken by Doug Benn in the 1990s of the site where the Bolton and Hindmarsh experiment was undertaken in the 1970s after the ice had disappeared. So in order to test the Bolton and Hindmarsh theory, you should be able to find their signature of A and B horizons in the geology. And that's effectively what Doug found. He found this open framework A horizon above the penknife, which is that's the A horizon ductile deforming material, and the more brittle deforming B horizon. Hopefully you can see the anastomosing shears running through this, which is the deforming B horizon. Okay, so far so good. We can relate process to form, and we can predict what we're going to see in the landscape. Jeff came up with this model, top left, a theoretical model of how we might expand this up to ice sheet scale. So this is Jeff's diagram, which shows every glacier, or in this case, every ice sheet, has an erosional zone where it's removing sediment and a depositional zone where it's depositing that sediment. It simply does that because my basal shear stresses are dropping off to the margin. My sediment is being advected to the margin, and I'm then depositing my tills, which thicken as I go out towards the margin and ultimately manifest in push moraines. So far, so good. This is also Jeff's model, which shows how I then might produce stacks of till relating to different events, advanced events of one ice sheet, to produce a complex sequence of tills at the margin. And that relates back to what we identified in the mid-1990s at Iceland. So if you like, we were testing Jeff's model and we came up with verification of that, which that appears to work okay. So let's then now take this up to the sedimentological and stratigraphic record of glaciation, and then look at what I like to now call tills and glacier tectonites. I didn't invent the word glacier tectonite, but I've certainly become a champion of the word glacier tectonite in the last 10 years or so, because I think that the shearing that takes place of the ice bed interface, the glacier tectonics that takes place at the ice bed interface, mostly produces glacier tectonites rather than what we call tills. And those are deformed, pre-existing materials. So just by way of introduction, by using another Icelandic example, this is a series of push moraines. These are Bob Price's 1960s push moraines, actually, the ones I showed you on the aerial photograph earlier, where we can identify A and B horizon tills, but underneath those, a whole series of glacier tectonized stratified sediments, previously glacial lake sediments. This is on Breiðamerkurjökull, same thing, one of our overridden push moraines again. A and B horizon till carapace, underneath it, pre-existing what we think are estuarine mudflat deposits with peats in them, with beautiful overthrusts and liquefaction along the thrust in relationship to the overrunning of the sediment. So this is what I would call glacier tectonite. And the more I deform it, the more mixed up it becomes. And if I keep deforming it, I homogenize it and I will create a till. A lot of the time, what we're looking at are the remnants and the recognizable remnants of pre-existing sediments. So if we wanted to test that, we need to go and have a look at these tills in more detail to see whether or not I can produce a till that's thicker than 50 centimeters, because that's pretty much what we're looking at in these experiments. And this is an example from a plateau ice field in central Iceland, where near the margin, near the Little Ice Age margin, you actually see this sequence, which for me, in terms of things that I think are actually real tills, this is about as thick as they get. And in this particular sequence, we've got, if we go from lithophases 2 to lithophases 8 through the sequence there, these are all individual till units. And some of them are separated by lodged clasts, or boulder lags, if you like, clast lags, these guys in here. And every now and again, you'll see a clast lag, which separates them. They're essentially a lag because the finer grain sediment has been advected or deformed away from the site. So by coming up with a summary of a whole range of things, and again, I won't bore you with the details, I've measured more class macrofabrics, I think, than I care to mention. I need to get out more, probably. But if we have a look at these sequences, we see that we can explain the evolution of the tills by the cannibalizing of B horizons by A horizons, whereby the A and the B horizons expand downwards and can thicken and cannibalize underlying materials, glacier fluvial materials, for example. And ultimately, we can produce these overprinted signatures of tills, A and B horizon tills. But we're never going to produce anything thicker than this unless we start really replicating them and thrusting them as thrust stacks or deformation sequences. Again, I'm not going to bore you with the details here, but we've summarized the types of tills we see in Iceland in terms of modern glacial systems and the types of tills that are created. So at the top here, these is thin tills on bedrock. We get bedrock poking through these thin tills, these little buried roche-moutonnées, and we get the tills filling the gaps in between. The lodge clasts here, which are presented that represent our lags or remnants. Overridden moraines, where we can override those multiple stack sequences and streamline them. And this particular case, what we call a push moraine complex. This is what one of these would look like if it hadn't been overrun. So this is like the one I showed you earlier from the mid-1990s re-advance. So I'm stacking individual till units. So if you like, I can go through each one of those till units and I can say that's 1 year's worth of till deposition in each situation. Now, we can talk for hours on this. This is all till strengths and till deformation. I am not going to bore you with the details of that tonight. That's for another time. Now, ultimately, then we come to what it is that we need to be finding in the geological record. What is the signature of glaciation? So we have our A and B horizons. This is Doug's photograph showing our A and B horizon, which we know is related to a particular process, subglacial deformation process. And here we have our glacier tectonites. Doug, Ben and I came up with this scheme years ago. I have to give credit here to Peter Banham, who came up with this sequence originally. He called these exodiametric glacier tectonites. And Doug and I came up with this classification whereby if we can subdivide subglacial till into A and B horizons, we should be able to do the same for glacier tectonites. So type A glacier tectonites are those which are most deformed, and type B, the least deformed. So I should be able to see fold structures and thrust structures and the pre-existing sediment clearly in a B, type B, in a type A. I start to attenuate them and streamline them more before I get to the homogenized version, which would be my till. I've thrown this one at the top because it's a nice example, one of the few places where you can find a nice example of the full sequence. So deformed sediment, boudinage sediment, so this refers to the deformed sediment, lake sediments in this case, boudinage sediment, and then homogenized sediment. And this is a sequence which is at the base of the Horden Till, which is on the Durham coast. So they're called glacier tectonite till successions, if you like. Now, when we first came out with a model in Iceland, we applied it to a very well-known case study around Loch Lomond. This is the Drumbeg Quarry. and South Loch Lomond. Doug Ben and I did the work on this a number of years ago. And we identified glacier tectonized lake sediments, which are these guys. You can see these guys are all boonanaged and deformed from left to right. There's our till carapace over the top. And the till carapace is made up of a series of slabs of till separated by thin, discontinuous streamlined bodies. And that's what they look like when we draw them out. We looked at some thin sections as well. And these, we think, represent the emplacement of slabs of till in the geological record, in this particular case relating to the Younger Dryas or the Loch Lomond Stadium. Okay, let me just give you another modern analog or two, and then I'm going to go into some paleo ice sheet stuff and give you a rundown of how we use all this in paleo ice sheets, paleoglaciology. I've talked to you mostly about warm glaciation so far. It may seem a bit odd to talk about warm glaciation, but it's warm, it's temperate glaciers. If we go to cold glaciers and subpolar glaciers, we see quite a different signature. They're not very good at depositing tills, for starters. And most of the time, the work they do relates to the meltwater that comes from them when they start to melt. So these are based upon subpolar glaciers and polythermal glaciers, mostly in the Canadian high Arctic, which is where I did my PhD many years ago. And we know we've got a polythermal glacier or a cold-based glacier when we get multiple meltwater channels inset within one another along the ice margin, because the meltwater can't penetrate to the bed. It runs off the surface and around the side. So it produces inset sequences of meltwater channels. At the same time, the amount of debris which is frozen into these glaciers is so huge that we get thick sequences of debris-rich basal and end glacial ice, which produces an awful lot of what we call controlled moraine, ridges of debris melting out of the glacier surface. And this little diagram here summarizes what we're looking at. So this at the bottom is an active temperate glacier with its recessional push moraines, which is what we've been talking about so far. At the other end of the spectrum, we've got freeze-on of the bed, freezing on of sediment, and large amounts of controlled moraine or supraglacial deposition in these glaciers. And a lot of the time, what we're seeing in terms of their impact are inset meltwater channels. So let's apply that to an ancient landscape. This is the margin of that glacier I just showed you. This is the Eugenie Glacier on Ellesmere Island. Those are the controlled moraines coming out on the glacier surface. If we look at ancient landscapes to look for that sort of signature where that's melted out, this is what we tend to see. And this is in the mainland Arctic Canada in the Tuktoyaktuk area. And believe it or not, the ice from the last glaciation is underneath this landscape. It still hasn't melted out, but we do see the controlled moraines and of course all the large meltwater pits in between. And Art Dyke and I came up with this model, which largely summarizes the recession of cold to polythermal glaciers from the landscape producing these sorts of signatures. Right, that's a whole range of modern analogues. Now let's have a look at what happens where things get complicated, i.e. things start to overprint one another as glacier activity changes or the glacier dynamics change or thermal regimes change over time. Because glaciers don't always retreat in the same way. The geothermal activity their geothermal characteristics can change. So this is an example of what we call spatial temporal change. I told you the geographer. We'll have a look at spatial temporal change. So here we've got an example of a warm polythermal glacier in northern Iceland, which has also been surging. And so we can identify two land systems inset within one another here. Land system 1, which is mapped in here in the pink with a series of ridges on it, is this stuff, ice cored moraine, which was deposited at the Little Ice Age maximum. And inside that lies outside of an area of fluted and drumlin ice terrain. So that indicates to us that we had warm ice running into cold marginal ice, which is a typical polythermal situation. Inset within that is land system 2. In here, where we see a lot of these things, crevasse squeeze ridges, which indicate that there were two separate surges which took place during recession from the Little Ice Age maximum. Another example, in the active temperate glaciers, they also have different land system signatures because their dynamics are changing and the structure of the ice is changing over time. And these are some drone images of Palaeoglaciological in Iceland fairly recently, where you see that the push moraines now, rather than you map these out and say, right, the ice margin was there, then it was there, then it was there. You find that very difficult to do in these situations. You can see the moraines are extremely sawtoothed, things that we call hairpin moraines now, they look a bit like hairpins. And the reason they're doing this is because the ice margin is becoming extremely crevassed by longitudinal crevasses as it downweights and splays. And so therefore, over time, the pattern of moraines has changed from what you would expect to see, these nice concentric rings of marking recession of the margin, to these overprinted fingers of ice producing all this inset, what we call sawtooth moraine, extreme sawtoothing. So what's happened here is that we are changing the drainage conditions to increase the amount of squeezing over time. Things are getting wetter, but we're also producing more radial crevassing in the ice. Right, I'm just going to finish off now with some examples and to show you how we apply this to paleoglaciology, quaternary paleoglaciology. John mentioned Brit Ice earlier, and I think probably a number of people will have heard of Brit Ice. And Brit Ice we started back in the 2000s to compile a glacial map of Britain, because to our embarrassment, the Canadians have got a glacial map, the Americans have got a glacial map, Scandinavians have got glacial maps. We didn't really have one. So this is why we, in 2004, 2005, we came up with these summaries, which were maps of our glacial features. And we came up with this thing here in phase 2 of that, which was published just recently, 2018, in the second phase of Brit Ice, which was called Brit Ice Chrono, which was our attempt to date the ice sheet recession. So that was our first attempt in 2004. By the time we got to 2021, we'd increased the amount of landforms on our map, our glacial map, and now we've got something we can be proud of and we can compare to those which have been compiled in other glaciated regions. The output, the final output of Brit Ice Chrono is this paper here with the cast of thousands. Chris Clark was the overall in charge of this. And these maps are merely here to show you where we collected materials for dating. So these are all our new dates, various dating techniques to come up with a reconstruction of how all this geomorphology goes together, how the whole ice sheet works. So this one, I'm hoping, yes, it will work. Look at that, marvelous. So this is the modeling output, the new modeling output based upon Brit Ice Chrono. So this is the summary of the evolution of our ice sheet, which is now moved on a little bit from the Hubbard et al. 2009 model. It's not hugely different, you know, because the ice is behaving in the way we would predict it to behave. But now we've got the control on where the ice was in terms of the geomorphology and when it was there, based upon the dating process. Okay, so if you want to catch up with all that, and you get beautiful printouts that you can get on the with the paper in the paper 2022, that's a summary of the Brit Ice Chrono project. I think we published something like 30 odd papers in relationship to this, so you can take your pick about which bit of the British Isles you want to look at in terms of the reconstructions. Right, okay, let's have a look at examples in relationship to the British-Irish ice sheet then, and put some things together. Remember Jeffrey's model here, so we're going to apply that to this bigger case study. I'm just going to show you some examples from the North Sea lobe in here. That's because I was in charge of Transect 2. It's the most interesting Transect 2, which is the one that comes from Scotland all the way down to the Norfolk coast, and it relates to the recession of the ice from Norfolk to Scotland. But I'm going to have a look at just one area in terms of the sediments and stratigraphy in relationship to that. This is a digital elevation model of Holderness. This is the Holderness coast, and all the hummocky stuff you see in here is effectively the end moraine of the last British-Irish ice sheet in that area. So by looking at the till lithologies here, matrix color, geochemistry, provenancing, we can see that we've got a very complex set of tills which have been vectored to the margin pushed on shore into Holderness. And it has different trajectories of ice coming on shore that produces individual packages of what we like to call dimictons before we make the genetic interpretation of till. And those essentially represent what Geoffrey would refer to in his model as advanced tills and retreat tills. So you produce tills during advance and then tills during recession. Let's show you what we mean by that. On Holderness, we have this is the basic stratigraphy. We have LFAs 1 and 4 are what used to be called the Skipsea and Withensea tills. I'm sure many of you have heard of that term before. Then we had subaqueous fans deposited from the ice margin and in the proglacial lake, LFA 2, and then glacier fluvial outwash was LFA 3. And so by using all these various logs and reconstructions, we came up with this very complex sequence of pulses of sediment being dragged on shore and partially overprinting one another in the same way that we see those models from modern glacier settings. And more importantly, this is something we're still working on. When we look at the tills, this is the Filey till in Filey Bay. When you look at the Filey till, I think all of you can see that that's stratified, yeah? And tills aren't stratified. So therefore, very simply, the message is it's not a till. So the Filey till is actually proximal glacial lacustrine sediment gravity flow deposits. And quite often the dimictons we see in these sections are sediment gravity flow deposits, cohesionless or cohesive debris flows, which are then glaciotectonized to produce glaciotectonite. So this is a setting. There's our ice. This is one of Doug Ben's diagrams. I think he used this one to illustrate Achnasheen, the Achnasheen Delta, actually. And so we're looking at that sort of setting in a much larger scale in Holderness, and where we look at the tills themselves, the stratified sediments are picking up the switch from subglacial deformation to subglacial sliding, subglacial deformation, sliding, subglacial deformation. So we can pick up these situations whereby the ice is either being lifted from its bed, is sliding, or is making contact with bed again to produce a deformation signature. And it is advecting this sediment to the margin to feed these marginal stacks in the glacier fluvial outwash. The next reconstruction I'd like to show you is, and this is going back to what I talked about right at the beginning, Kame and Kettle topography. Many of you may know of the Brampton Kame belt, or certainly you may have driven through it. Brampton is up in here. That's Talcon Tarn, which is the big, was supposed to be a kettle hole in the middle of it all. I wouldn't argue with that. And the digital elevation model here picks up this stippled pattern, which is this hummocky topography, but running through it all, there's a whole load of Kame and Kettle topography in here, but running through it all, a whole series of sinuous ridges, which have got to be eskers, which have emerged through the down-wasting ice. This is just the image in 3D, looking back towards the North Pennines. And this is the model that we came up with, which is basically a glacier karst system, which is effectively applying the model we had from Iceland to this situation in the Brampton Kame belt. So this is what we're looking at. This is an aerial photograph. The glacier margin there, Sandfell's Jokel is top left. This is ice marginal sediment, glacier fluvial outwash deposited over the ice, slowly melting out to produce the big kettle holes. This is a big shadow, by the way, from a mountain, ignore that. So this is terraced outwash, or what we might want to call Kame terraces. Birkes Jokel in here, Andrew Finlayson will recognize this for sure. So this is a endglacial esker coming out, feeding outwash onto superglacial settings. So it's exactly the same model that we've identified at the Grote Jokel, which I showed you earlier, whereby we have this burying of glacier margins and then the melt out of that underlying ice to produce our Kame and Kettle topography. Thought I'd give you something a bit local. This is something we did a couple of years ago. Again, this wasn't initiated by us. This is the map. Again, you geologists might recognize these maps. Map from the Mineral Assessment Report, pink guides, the pink books. And this is for Strathallan. And the area in the darker pink here is the glacier fluvial deposits, the thick glacial fluvial deposits that are usable for aggregate resources. And this is the Digimap compilation. So this is Strathallan in here. And what I want you to look at here are the inset sequences of meltwater channels up here on the valley side, feeding into the outwash on the valley floor. and the meltwater channels on this side in here. So when we map those up onto a digital elevation model, hopefully you can see all this. That's Braco at B in there. Glen Eagles is here, which Bob Price years ago identified that the fairways in Glen Eagles are pretty straight and run parallel with one another. And the reason they do that is because they're in between esker ridges. So the meltwater channels up in here, these are the meltwater channels on the ground. We have little eskers that are coming from those channels. This esker in this particular case has been what we call subglacial engorged. It's gone back under the ice in the nearby valley. And we think what's happening here is a bit of this, which is back at our Iceland, burying our ice margins. But in the earlier stages of melting, these meltwater channels must have been this sort of situation. So the ice margin must have been cold at that point. And interestingly, when now we've got Brit Ice chrono, and we know roughly at what time the ice was sitting here in Strathallan, we know that that is around about 15,000 years ago, and that is bang on the Western Ross re-advance. So we think that the meltwater channels might be identifying particular events during the last glacial cycle for us. We've done a similar thing down in, this is where I live in Teesdale, and this is a digital elevation model. This is Teesdale here, tributary Loondale. Inset sequences of meltwater channels, they really are beautiful. This is what they look like in the field. They're cutting down through a whole series of drumlinized terrain. And these guys, based upon the cosmogenic nuclide dates we're getting in the area, indicate that this is probably a Scottish re-advance age, around about 19,000 years. So I knew these meltwater channel clusters in Britain were telling us something years ago, but I didn't quite know what. But based upon our Arctic examples, I knew they must mean that the ice margin had gone cold for a period. Now we've got the dating, we can see why the ice margin went cold. It's related to particular re-advances during the overall recession of the ice sheet. Okay, I just want to finish off with one of my favorite places on the planet, which is the Laurentide ice sheet, and various places around the Laurentide ice sheet that I've worked over the years. But I just want to concentrate on the warmer bits, which are down here in Alberta. And this mass of overprinted paleo ice streams in the Laurentide ice sheet. So we're just in this area in here. This is a recent compilation by Margold et al. The details of the ice sheet overprinting in here are based upon some research we've been doing over a long period of time in Alberta. And it helps us use our modern analogues to apply to these much older glacier reconstructions. And to cut another very long story short, I'll give you the digital elevation model of most of Alberta and Saskatchewan, and on it you can pick out the former pathways of ice streams in the ice sheet based upon fast flow indicators like megalineations, like super big flutings. And when you map out the different landform types, you can identify recessional push moraines on the aerial photographs. They represent active recession. You can pick out enormous thrust moraines. These guys are like 70 meters, over 70 meters high, individual thrusts within Cretaceous bedrock, which have been created by the ice re-advancing rapidly. So we interpret that as a surge, especially because inside of them, in places, we can see crevasse squeeze ridges, the biggest crevasse squeeze ridge you've ever seen in your life. Everything's bigger in North America, obviously. And so these guys represent ice sheet, ice stream surges. And also in places, we see situations where hummocky moraine and what we think are controlled moraine ridges based upon cold polythermal conditions switch to active temperate. So if we go back up through flow, we go active temperate, cold based, active temperate, surging. So our ice sheet response, the dynamics of the ice sheet are changing over time based on our geomorphology. So just to give you some examples of what that looks like, and this is just also to show to you that we shouldn't be throwing aerial photographs in the skip, okay? These are aerial photographs that were taken in the 1950s of southern Alberta. They're mosaics, so they've been stuck together to mosaic them up. And at the time, you can see agricultural improvement, but agricultural improvement didn't involve big plows digging down 3 or 4 meters through the surface. So that meant that you could pick out individual push moraine ridges which are 18 to 20,000 years old, and they're only a meter or two high. And as you map these out, you can map out zones where we switch And this is just an example of my mapping for you. You switch from these coherent push ridges to more chaotic patterns. And when you look at them in detail, we have different types of ridge. These guys are controlled ridges, which indicate cold climate conditions. These guys are flutings with push ridges, which represent active temperate. And these guys are overridden ridges, where we've got ice overriding pre-existing moraines. And when you map them out in a series of zones, you can work, this is a theoretical diagram, this one, but it does apply to this case here. We're changing the dynamics of the ice, the thermal dynamics of the ice based upon the geomorphology. And then we switch to the surging. And so these are the big surge moraines in bedrock. This is what it looks like in road cuttings. That's Cretaceous bedrock, which has been folded there by re-advancing ice. These are crevasquez ridges, so you can see roads in here for scale. These guys are up to 6 meters high. And they all fit into our model of surging. So we can see that in the ancient landscape record. And this is what we think the ice loads are doing. That's what they do early on. They keep fairly consistent surging in the same place. And then during the later stages of deglaciation, they switch to surge mode and they overprint one another. Right. That's got me to the end. I'm just going to leave you with something that we are moving forward with at the moment, which is also based upon Alberta. And this is another game changer for us, which I've already mentioned there before, LiDAR imagery. At the moment in the UK, we can get access to LiDAR that's been flown along river valleys only. And it's not necessarily always the greatest of quality, but it's still good. In Alberta, good old oil-rich Alberta, the whole of the province has been covered by high-resolution LiDAR. And if you know the right people, and right people to talk to, you can get some of this stuff. And this is what it looks like. So as I say, this is an absolute game changer. We are now picking out features in the glacial geomorphology which we never really saw before. And some of these, this guy here, hopefully you can see, which I've outlined with a dotted line. You can see that this stippled pattern, which is the Cayman Kettle topography, is slightly muted. And that's because there is what is called an ice-walled lake plain has been developed on the ice, like a saucer full of water. And as the ice is melted, the sediments in the ice-walled lake plain have just been draped over the underlying material. That's a big thrust block moraine in the top left, the same one again that I was showing you before. This guy here is again Cayman Kettle topography, but notice these are not just circular pits which are opening up as the ice melts underneath. These guys actually have linear margins to them, and many of them you can see are arcuate. And this is what you see at point X. This is what you see in the stratigraphy. Glacier tectonites, sediments which have been heavily disturbed, in some places hydrofractured and deformed by loading. What we think is taking place here is the ice is surging and re-advancing back into buried glacier ice covered with sand and gravel, which I think hopefully you can remember back to the first thing I showed you. That's exactly what we see in the historical record in Iceland. So we have a bit more confidence about applying it to stuff that's 20,000 years old. And so this little model here is really taking things forward in terms of how the Clayton and Moran model I showed you right at the start, the process form model from 1974, this is taking it to the next stage where we identify that some of the complex features we see, the really complicated features, are actually related to surging and re-advance back into buried glacier ice with its own glacier cast developed within it. So that then you're seeing several phases of geomorphic activity playing out in one. So hopefully we're now starting to move towards explaining some enigmas which have worried us for a long time, but it's always the case that we end up finding that we've seen it. We've seen it last year while we were in Iceland with our students. We saw something evolving on yearly scales and on the aerial photography. And again, you have to take a step back, look at what you've got in the record for older glaciations and try to apply those modern analogues. I don't think we're going to stop learning from that. That's the important message. Okay, just a final thank you. Thank you for bestowing this medal on me. It's humbling, but at the same time, it's very nice to know that I've received a medal named after a guy who was a meticulous field worker, an observer and mapper, which is basically what I've been trying to do since I did my master's, my peers photographers of me doing my field notes in the days when I had hair in the mid-1980s doing my PhD. And from that, and I was always taught at that time that those observations, those smaller scale observations, the meticulous observations ultimately make a much better reconstruction towards the end. And so in some situations, it's taken me 20 odd years to work out that I don't think meltout till exists. You know, it takes a long time to come to some conclusion on things, but you've got to think about it for a long time. So for that fact, I thank you very much.